Okay, in this video, we are going to see some more methods for calculating the enthalpy change. So in the previous video, actually we have gone through a method called enthalpy change cycle for calculating the standard enthalpy change of a reactions. So in this method, actually we base on that one, and we have a very simple and actually a simple equation for such kind of calculation. So let's start. Okay, so first of all, in this example, we are going to calculate the enthalpy change of the following reactions over here. So, but of course, before we do the calculations, we need to take a look at the data information given over here, which is important. And of course, we need the thermochemical equation as well. So let's write the thermochemical equation for this part. So this is formation of C2H4, which is the ethene. So C2H4 is formed from carbon and hydrogens. So C2H4 over here, and we balance it. To simplify, to shorten the time for the steps. At this moment, and in this part, actually, we try to neglect all the state symbols. So this enthalpy change is positive 52.3. So for the next one, formation of C2H6, which is ethane, C2H6. So 3 hydrogen gas plus carbon. So the enthalpy change would be negative 84.6. Okay, so according to what we have gone through in the enthalpy change cycle, we need to take a look at the given reactants in the above thermochemical equations there. So first of all, let's take a look which one feed the thermochemical equations upstairs. So you can see C2H6, actually this feeds these thermochemical equation. So we can actually use an arrow, copy the thermochemical equations here. So C2 carbon, sorry, it should be 2 carbon, not a balance. So 2 carbon plus 3 hydrogens becomes C2H6, and this is actually equation 2. Okay, so what about thermochemical equation 1? So we have the product C2H4 over here, and you can see 2 carbon plus 2 hydrogens would become C2H4. So the green color one is actually the third thermochemical equations. Okay, now let's take a look. So we try to label each enthalpy change for each equations. So this is delta H, and then this is delta H1, this is delta H2, and this is delta H3. Do you still remember how to calculate by using the enthalpy change cycle? So we need to find a common starting point and a common ending point. So let's take a look. So from my point of view, this is the common starting point, and that one is the common ending point, because you can see we have 2 roots, just like what we experience in MTL. If we start from the same station and get off at the same stations, even though you are using different routes, you have to pay for the same fees for that one, for the ride. Okay, so the first route would be like this, and it reached the destination over on the top right hand corner, C2H6. So this is route number 1, and this is route number 2. So that's the reason why you can make this equation delta H2 plus delta H1 equal to delta H3. Actually, we would like to calculate delta H1, therefore we need to make some changes on the subjects in the equation. Delta H3 minus delta H2. So we plug in all the information here. So this is delta H2, and this is delta H3. So delta H1, which is the enthalpy change that we are calculating, is equal to negative 84.6 minus positive 52.3. Now can you see, actually I have some tips for you so that you will not mix up the plus and minus sign in your calculation. Remember, what I did is I copy the number including the positive sign into this part, and the negative sign is coming from the equations over here. So you can see negative 84 so it is equal to negative 84.6 minus 52.3. So 84.6 minus 52.3. So the answer will be negative 136.9 kilojoule per mole. So this is the original method that we use in the by using the enthalpy change cycle. Okay, now please press pause in the video. Try to take a few minutes, take 3 minutes to work out the same thing by using enthalpy change cycle for the following questions. 3 minutes. Then let me show you the answer. Okay, now let me show you the answer. Let's go through it once again. Okay, so we need, for the formation of PbO here, we need the equation Pb plus O2 becomes PbO. Remember, we need 1 mole for the product form, which is PbO. Therefore, in this kinds of balancing, we need to use fraction to make oxygen on the left of the equation become 1. Okay, so the enthalpy change for that one will be negative 220. So I'm not gonna copy it once again. Okay, next one, we have another thermochemical equation for the second one. So Pb plus O2 becomes Pb3O4. So we balance it by putting 2 and putting 3 over here, and the enthalpy change will be that one. And let's work out this together again. So remember, try to find some common thing in the thermochemical equations when you're dealing with the equations with the enthalpy change that you need to calculate. So this is what we need. This is our target. Okay, now let's see. So we have Pb3O4 over here. So it is the same as the second thermochemical equations. But can you recognize one thing? Actually, we have 2. We have number 2 over here. 2, that means we need to form 2 Pb3O4. So according to the equation above, it's just form 1. Therefore, we need to make it become 2. But if you put 2 over here, it is not really fair. Therefore, we actually need to multiply the rest of them. It becomes 4. It becomes 6. So it's just like the whole equation multiplying by 2. If you multiply the second equations for this one by 2, don't forget to multiply the numbers by 2 as well. So you get the equation already. So it will be 6Pb plus 4O2 become 2Pb3O4. Okay, let's see how we use the third thermochemical equations over here. So the third one is actually the same as 6PbO over here. You can see PbO here. But we need 6. That means we have to multiply the equation by 6. 6 over 2, that means 3. 6Pb. So you can see it becomes 6PbO. Wait a minute. We get 4O2 here. 4O2 over here. Actually, how can we balance? You can see there's an oxygen over here. So that the equation is actually balanced right now. Okay, so we do the same thing. We labeled delta H1, delta H2. So this is delta H1, delta H2, delta H3. And don't forget, actually, I made a mistake in the above enthalpy change cycle. I forgot to put state symbol. Every time you work out the enthalpy change cycle, don't forget to put state symbol. Okay, alright, so let's take a look. So you can see, again, we need to find a common starting point, which is this one, and common ending point, which is another one. So we get how many roots here? We get 2 roots from the same starting point to the same ending point. So this is roots number 1, roots number 2. Okay, alright, so that means delta H2 plus delta H1 equal to delta H3. And what we are calculating is delta H1. So delta H3 minus delta H2. And then we try to plug in all the information from the above. Don't forget delta H3 has to be multiplied by 2. Or that means this one. This is delta H3. And this is delta H2. Okay, alright, let's take a look. Negative 737.5 times 2 minus negative 220 times 6. Okay, so the answer is negative 155 kilojoule per mole. Alright, so this is how we work out the second one. Okay, now the reason why we work out this one together because we would like to find out something common in these 2 examples. And when you go back to the equation for the calculation, can you see the equation for these 2 are actually the same? What make this equation for calculation the same? Take a look at the given data over here. The given data here is formation, regardless of what we are calculating. And the next question here will be formation again. So can you see one thing in common? Whenever the data, I mean the numericals data given in the questions, whenever it is a formation, you can use this for the calculation. You can make use of the formation of the product, which means PbPO4, minus formation of the reactant, which is PbO. Over here, the same, you can use the formation of C2H6, the product, minus the formation of the reactant, C2H4. So actually, this becomes a very, very useful equations for the calculations. So we get this one. Whenever you want to calculate something, but if you see the numerical data, I repeat, numerical data, the numbers given to you in the scenario, in the questions, whenever you see this one, whenever you see all of them are formation, so you can make use of this sum of. That means this is sum of. Okay. So whenever you see this sum of all the products minus sum of all the formation of reactants. So let's make a conclusion again. So the situation here would be all numericals data. All numericals data should be formation. If this is the case, you can use this equation for the calculation, because the reason why they find this equation is they work out so many enthalpy change by using data from the standard enthalpy change of formation. They use the numerical data from the formation, and every time they do it, they get the same results. Therefore, this is actually a way to calculate standard enthalpy change, the standard enthalpy change by using this method. So if you know this method, you don't need to draw the enthalpy change cycle again and again, because you can make it very simple. Take a look at the target that we have to calculate. So find the target. This is our target. The target that we would like to calculate is this one. And what's next? We find all the formation of the product. So this product formation, the formation of Fe, wait a minute, formation of element is actually 0. But for this one, we have negative 393.5 here. And then for reactants, we have it here. Fe2O3, negative 822. And then for carbon monoxide, we get negative 110.5. But don't forget, because in these equations, you can see 3 CO2 is formed. That means the equation will become, that means this one should be multiplied by 3 because it forms 3 CO2. From the definition of formation, it's just telling you 1 mole of CO2 is produced, but right now we get 3 moles of CO2 from the target equations. Therefore, don't forget to multiply it by 3. Okay, for the reactant, we do the same thing. You can see 3 in front of CO, so we have to multiply by 3, and then there's a hidden 1 here, so you don't need to multiply it by 1. It's just 1, okay? So, next one. The calculation will become very straightforward, very simple. So, the enthalpy change for that one, enthalpy change will be equal to, you don't need to show 0 over here. Actually, don't need. If you want to show it, you just show it, doesn't matter. So 3 times negative 393.5, and then now minus, okay, pay attention to this one. This is quite easy to make mistakes here. It is quite easy to make mistakes. So don't forget to use more brackets for that one. So Fe2O3 will be negative 2822, and then plus the sum of the reactant, all the reactant, plus CO will be negative 110.5 times 3. Don't forget to times 3. Okay, so you use this equation to calculate. 3 times 393.5, negative 393.5, and then 822 minus 822, 110.5 times 3. So this one should be negative 1153.5. And then this one will be negative 1180.5. So the equation would become 1153.5. Okay, it's negative 27 kilojoule per mole. Okay, let me check. Okay, it's negative 27. So this is how we use this method for calculations. So this is the method only be used when you see all the numerical data. What does that mean, numerical data? This is numerical data, numerical data, numerical data. Regardless of what you are calculating, you need to take a look at the numerical data. Yeah, this is numerical data, numerical data, numerical data, numerical data given. And that's why we call it from enthalpy change of formation, regardless of what you're calculating, what kinds of enthalpy change you are calculating. Okay, alright, so this is a method if you see this. Okay, let's see another way for calculation. The second part will be quite similar, to be honest. Quite similar. Okay, so this part very similar, except one thing. You can see all the data, numerical data given is combustions. And in this case, it always you're always calculating you're calculating the equation for formations. But okay, wait a minute. Let's try to work out the example 1 together. Okay, so alright, let's take a look. So you're going to calculate the enthalpy change of formation of methane. Wait a minute. Don't mix up with the previous method that I showed you just now. Even though we are calculating formation, don't make a wrong judgment. You're using product minus reactant. No, don't mix up. because we need to see numerical data, okay? Anyway, we take a look at the enthalpy change cycle first for this one. First of all, we need the target. The target equation that we are calculating would be the formation of methane, C plus 2H2, become CH4, done, okay? And then we take a look at the above equations and we try to see which thermochemical equation fits the targets. Okay, now let's take a look. Carbon, graphite, it fits this one. So I rather put it here, oxygen becomes CO2. So this is delta H1, delta H2. Oh, sorry, no. We do the labeling later. Okay, next one, we get another one. H2 is over here, so it comes from the second thermochemical equation. But you can see hydrogen H2, you have to multiply it by 2 because we need 2 hydrogens in the target equations. Okay, alright, so 2, the whole equation multiplied by 2, and don't forget to multiply the numbers by 2 as well. So plus oxygen become 2H2O. Okay, next one. The last equation over here, it should be used over here. See? So CO plus 2 oxygen becomes CO2 plus 2H2O. It fits the third thermochemical equations. So it's done. Let's take a look how to label them and calculate the rest. Delta H1, delta H2, delta H3, and this is delta H4. So this is 1, 2, it should be 2, 3, 4. Equation 2, delta H2, 3, 4, okay? Okay, once again, for enthalpy change cycle, the second last step is to find a common starting point and common ending point. So let's take a look. So from my point of view, I think this is a common starting point, and then the bottom part is the common ending point. Let me share with you why. So the first root would be number 1, and then number 2, you get to the destination. This is root number 1. And then second root would be this one, go directly from the top to the bottom. This is target root number 2. So let's try to write out the answer. Delta H1 plus delta H4 is equal to delta H2 plus delta H3. Okay, so what we are calculating is delta H1. So let's change the subject. Delta H1 equals to delta H2 plus delta H3 minus delta H4. So let's plug in all the numbers together. So delta H2 would be negative 393.5. Delta H3 would be negative 285.8. Don't forget to times 2 plus negative, not plus. My thought should be minus negative 890.4. So the answer is negative 74.7 kilojoule per mole. Okay, so this is example 1. Now, for example 2, actually it's just repeating the same thing, trying to use 3 minutes to work out the enthalpy change cycle so that we can find out some common thing. So please pause the video before you see the steps for this part. Okay, alright, so let's try to go through the steps. So your target is to find out the enthalpy change sign at the formation of ethanol. So ethanol C2H5OH. So from the constituent element 2C plus 3H2 plus 1/2 O2. Okay. So let's try to fit in the thermochemical equations. First of all, we have carbon, which is the same as this one, but we need 2 carbon. Therefore, times 2 times 2 times 2 times 2 for the enthalpy change for the enthalpy change for that one. So plus 2 oxygen become 2 CO2. And next one, we get 3. Wait a minute, this is a typing mistake here. It should be 1/2. It's a missing part. So 3H2, 3 over times 3, and then times 3. The enthalpy change also times 3 for that one. So we get this one plus. So we already use up 1/2 oxygen here. Therefore, we just need one oxygen. Add up together with them, together with the 1/2 oxygen here. So we get 3H2O. So 0.51 here, add up together should be 1.5. So it will be the same as that one. And then the last one here is shown here. So you get the last one, C2H5OH, the same as that one. So you get plus 3 oxygen becomes 2 CO2 plus 3 H2O, the same over here. So you can see, you can double check with your enthalpy change cycle. You can see this number of oxygen added up is the same on the left and the right hand side over here. So that means you get the correct enthalpy change cycle. Okay, let's do the same thing. Try to label them one by one. Delta H1, delta H2, delta H3, and delta H4. So same, find out the same starting point and the same same ending destination. So this is the starting point, this is the destination. So you use root number 1 and you use root number 2 over here. So you can see they all come to the same destination from the same starting point. So let's do the calculation. Delta H1 is equal to, delta H1 plus delta H4 is equal to delta H2 plus delta H3. Okay, so we change the subject. Delta H1 is what we are calculating. So delta H2 plus delta H3 minus delta H4. So let's finish the calculation. So this is delta H2, 3, and 4. Am I right? 2, 3, and 4. Okay, 2, 3, and 4. So number 2, don't forget to multiply by 2. 393.5 times 2 plus delta H3 negative 285.8 times 3 minus negative 1371. Delta H4 393.5 negative times 2 plus 285.8 negative times 3 plus 1371. So we get negative 273.4 kilojoule per mole. For delta H1, this is the enthalpy change that we are calculating. Okay, so we have come across 2 examples in this part, and you can recognize actually the numerical data given would be combustion, combustion, combustion. The same as what we can find here, combustion, combustion, combustion. So because of this, you can see the equation now become the same. It's just like reactant part add up together, reactant part add up together minus product part. Same here, reactant part minus product part. So you get the same equation over here. Therefore, the conclusion is whenever you see the numerical data in combustion, in the enthalpy change of combustions, you can use this way for the calculation. You can add up all the enthalpy change of combustion of reactant minus the sum of all the enthalpy change of combustion of products. That's it for this kinds of that's it for the second equation that we generate. Remember, this is actually a short method a quick method for you to calculate the enthalpy change only when the numerical data given is combustions only. Don't mix up, do not mix up. or this method helps you to check your answer in your calculation as well. And of course, it's a good way to solve some of the questions. Okay, so this summary actually is not that important. The most important part for this, most important thing here is whenever you see combustion, reactant minus product, okay, the numerical data. And for the above, wherever you see the data is formation, remember product minus reactant. And to be honest, I use the definition to help myself remember this equation. You know, the definitions of enthalpy change of formation is 1 mole of product forms 1 mole of substance form. The substance must be a product. 1 mole of product form from its constituent element at standard states under standard condition. So product formed, substance formed. So must be product, starting with product, therefore product minus reactant. And for combustions, the definition of the enthalpy change of combustion is 1 mole of substance burned, to be burned completely at standard conditions. So the things that gonna burn must be a reactant. Therefore, combustions, enthalpy change of combustion, numerical data given, must be reactant minus product. So this is my way to remember these two equations, and it never is made up in my mind. So I think that's all for this method 2 and method 3, these two equations. So try to make use of this information and complete the rest of the questions in the Google form and also the worksheets.